give you a source resistance is equal to a load resistance of 200 ohms. And it wants to know, first, I guess we'll do the modes first, which makes logical sense. So first thing we have to calculate is the actual cutoff frequency for each mode, M comma N, and get the three lowest modes. So that's going to be C over 2, or 1 over the square root of mu epsilon divided by 2. Then it's going to be times M over A squared plus N over B squared. When you go through this, you can find the FC10 mode is the lowest, it has to be. And it was at, I didn't have this written down, can somebody just tell me this? I've got them over there.
6.56 gigahertz.
Yeah, 5.6 times 10 to the 9th hertz. The second mode, FC20, is at twice that, 2 times FC10. And what is that?
13.12.
2 gigahertz. And then the next mode is the FC01 mode. And
14.76.
now these are all TE modes. The TM mode would have to have both of these as non-zero. You would have two concurrent modes. You'd have both TE and a TM. Anytime there's a TE, there is a TM mode. Just keep that in mind. All right, those are the frequencies. After that, the next thing you get is K. And K is going to be the square root. Well, first of all, let me say this. What mode propagates only one this? Because that cutoff frequency is less than 7.7 gigahertz. The other two modes are higher than that, so only one mode propagates as expected. That was predictable. Therefore, K is going to be equal to 1 minus quantity FC10 over F squared. And I might add, like you can never have, if this thing was imaginary, if this number is larger than 1, then you have the square root of a negative number, you get a J. Anytime you have that, that mode can't propagate. Keep that in mind. What people sometimes do accidentally is they switch these. They put F on top and FC on the bottom. And then they'll get minus J something or plus J something, which is immediately when you see that, you know something's wrong. You've done something wrong. And can you give me the value for K?
0.5236.
Yeah. All this will put up on the window. So after that, then I'm going to get beta unguided, and that's just going to be omega over C. Y'all follow me? Because the waveguide is filled with air. So it would normally be, this is normally omega times square root of mu epsilon, because mu and epsilon are both free space, mu naught epsilon naught. It's just 1 over C. And I forgot, it's like 110 or something. The unguided value. Anybody?
161.27.
Is that right?
We weren't asked to solve it.
Well, but you need, well, you don't have to get it that way, but it's just this times K is going to be beta in the guide, right? Y'all follow me clear? You can get that a couple different ways. Anyway, beta in the guide is going to be beta unguided times K. And you can give that if you want.
84.44.
Beta unguided?
Beta guided. The other one is 161.27.
And that would be radians per meter. And this is 81, did you say?
84.
84.44. That would be radians per meter. All right. After that, we're going to get the impedance of the guide, the characteristic impedance that's going to be used in the waveguide equation. So the next thing is going to be Z naught. And Z naught is really going to be eta naught, where eta naught is simply equal to 125 ohms divided by K. And it's divided by K because it's T. If it was TM, it would be multiplied by K. Do y'all remember? And so I think that's 740, is it?
720.
720 ohms?
Yes, sir.
All right. Then after that, they wanted the input impedance to the waveguide. I think that's the natural order, right? we're gonna need this. So I come over here, and the input impedance to the guide is gonna be the characteristic, this is the characteristic impedance of the guide, times the load impedance, or resistance in this case, plus J, times the characteristic impedance of the guide, times the tangent of beta in the guide, times L. And L was 0.48 something?
Yeah, 482.
2 meters. Then divide that by Z naught plus JZL times the tangent of beta in the guide times L. And I asked that in polar, can you give that to me? I know most people, a lot of people got this right.
It's 224.27
224.27.
at an angle of 24.74.
Is that, everybody consistent, right? And so, that's this equation solved. Now that equation is usually troublesome. Did you all get about that? We know what's good. It's somewhere around there. I'm gonna warn you, it's pretty sensitive to this value. So if you round it, you'll get slight differences, but I give you full credit. If you didn't make an error or put ZL in front here, then Z naught here, because I gave you that formula to it. All right, after that, they want the volt, do I want the voltage at the input of the?
You're asking for the reflection coefficient first.
All right, let me just do this. This is 20 volts, I think.
It is.
Then here's the guide. I'm just showing it as a transmission line. And here's your load here. Our load, which is 200 ohms. And now the next thing they want is a reflection coefficient of the load drop. That's one of those that's just straightforward. It's just like transmission lines. So I take RL minus the characteristic impedance of the guide, the 1 ohm mode, over RL plus the characteristic impedance of the guide, the 1 ohm mode. And if you could give that to me.
Negative 0.56.
You all with me on this so far? Now we get the voltage at the input to the guide. I don't know if I asked for that specifically, but these are the steps you have to naturally take to get the final answers. Right? So then we're going to get V in, and that's going to be the input voltage right here, just on the other side of the waveguide into the guide, which would be here. And that is simply going to be equal to Vs times Zn over Zn plus R source. So Vs is 20, Zn is given as, where did I put
It's above the figure.
224, yeah, or so 24.7 degrees. So this is going to be this will be a complex number. What did you get for that?
10.83 at an angle of negative 11.63.
At an angle of what?
11.64.
That's an approximate value.
It's negative 2.
What?
The angle is negative.
Minus. Okay. With me on this, it's going to be about that. After that, you have to set that equal to V0 plus times, and this is going to be e to the plus J beta in the guide times L plus the reflection coefficient at the load times e to the minus J beta in the guide times L. And so to get V0 plus, you're going to have to divide this by those two complex quantities. And you'll get V0 plus equal to about 10.83 at an angle of minus 11.64 over, and it's going to be e to the plus J beta in the guide times L plus reflection coefficient times e to the minus J beta in the guide times L. And if you can give that to me, I'll put the whole thing up on OneNote.
22.22, an angle of negative 165 roughly.
Minus 165. Is that about what you got? So if that's V0 plus, then after that, they ask for the voltage at the load. I mean, you need this to get it, right? The voltage at the load, V at the load, will simply be equal to V0 plus times 1 plus gamma L. And so you're simply going to take that times this to get it. And can you give me that? And this will be approximate. If you have it.
Yeah, 8.581 angle is negative 173.
Now, I gave some tolerance there because there were some rounding. I mean, when you round a few numbers, they'll change about 10%. Okay, because this was that beta in the guy is very large. And then finally, they want power at the load, right? Now it's a pure resistive load, so power at the load is simply going to be 1/2 times the magnitude of V at the load squared divided by R at the load. And V at the load is that you forget the angle. Power always is strict real. You're not going to have an imaginary component unless you have reactive power. This is real power. So, and RL is 200 ohms. Can you give me that?
0.184.
5.184, is that right?
I got just 0.184.
0.1, well, that sounds better. 0.14.
0.184.
0.1, yeah, that's right. Once. And that should be your first problem in a nutshell. Y'all follow? Did you have questions about this anyway? Most of the errors that I saw on this had to do with really this equation here. Somehow, probably the old problem of radians and degrees, but I don't know that for a fact. I'm just telling you, I see the equation and the wrong answer. It's very hard for me to discern where the problem was, except it's in that equation. All right, that's the first problem. No way to do it. Second problem, by the way, these were created out of homeworks. I simply went through the homeworks, created these. I didn't try to do anything. If you actually look at your homeworks, you're going to see these things almost identical, except for different values of either distance or power or something like that. Problem 2. You have an antenna here with a transmitter gain of 30 dB, and then you have a distance of 10 kilometers. And then you have a dipole that is got a length L, 0.485 lambda, and it's connected to R equals 72 ohm load. And from this one, let's see, I asked for first is the power density incident on the antenna. So they want the power density right here. I want the power density right there. P average right there. And P average, always take the transmitted power over 4 pi R squared. That gives you the power density without any type of a gain enhancement, and times the gain. So transmitted power, let's put it here.
For 4,000.
4,000 watts? So that's 4,000 over 4 pi, and then 10 to the 4th squared, or 10 to the 8th, and the gain is 30 dB, so that would be a gain of 1,000 in linear quarters. So this is gonna be the actual power density. Can somebody tell me that?
3.18 milliwatts.
3.18, and that would be milliwatts per meter squared, right? That would be the units, because it's a density, yeah.
Can you do the 1,000 conversion for the gain?
Yeah, it's just a standard dB thing. When you have gain in dB, that's 10 times the log of the gain linear. You need linear gain here. So you're gonna take this gain and divide it, or 30, divide by 10, right? Then you take it to the 10th power, or you take 10 to that power, that would be a 10. That's gain. By the way, there were 2 problems with gain on it. And I gave you several where you had gain in dB, if you look at the homework. Matter of fact, I don't know how many I gave you, but, so that's a common way for this to work. So that's the average power density. After that, you need the actual power received. This is the power received that's not at the load, but by the antenna itself. So P received is really gonna be the power density we just calculated times the aperture of that antenna, which is lambda squared over 4 pi. And this would be the maximum gain, which would be 1 times 1.64. I gave you the gain equation, but because the angle is 90 degrees, it's the max gain, it's just gonna be 1.64. You didn't have to do any angular calculations. And, lambda for this one, I didn't put the frequency. Frequency is 500 megahertz, right? And that means lambda is equal to C over F, or it's 3 times 10 to the 8th over 5 times 10 to the 8th. Or it's gonna be 0.6, right? And, well, when you do this, can you give me the value for that? Because then
1.49 times 10 to the negative 4.
10 to the what?
Negative 4.
Is that right?
That's right.
Okay. Anyway, it's a straightforward calculation. Y'all follow me on this, guys? Make sure you know how to do this kind of problem. You'll see it on the final. I promise you. All right, so that's the amount of power received. Then you have to get the open circuit voltage. This would be the voltage that would be across these antenna terminals if nothing was connected. And VOC is simply 4 times the actual P received, right? Times, and then it's going to be the radiation resistance of the antenna. So that's the square root of 4 times that, which is 1.49 times 10 to the minus 4. And then it's going to be times the radiation resistance. I cut this thing down. You would have got it right if you put 73, but it's really, when it's 0.485, it's about 72 ohms. Then there's no imaginary part, so this is just 72. And can you give me that?
0.2075.
All right, that's the open circuit voltage. Then I'll build a circuit that represents that antenna right there. So here I have plus or minus V open circuit, which is given by that. Then I have the antenna impedance. Remember, there's no imaginary part when it's cut down to 0.485. And the antenna radiation resistance is just 72 ohms. And then I put this load down here, which happens to be the same, 72. On the final, I probably won't have these two equated, just warning you. So you won't be able to assume that that is going to be the internal resistance of the antenna, the radiation resistance. Now, taking one look at this, if you know you receive that much power, you can just deduce half the power is going to be dissipated in the load because they're identical values of resistance. Or what we can do is simply find the voltage of the load. Voltage of the load is simply VOC divided by 2. You don't agree with that? Has to be, right? Because the identical resistors are in series. After that, you get the power in the load, simply 1/2 magnitude of V in the load squared divided by R in the load, which is 72. And
7.48 times 10 to the negative fifth.
Okay, which is exactly half that power. Okay. All right, then, any questions about this one? No? All right, problem 3. So they give you, I have two materials. I have air here, and I have a wave propagating in this direction, EI coming in. And I have a material, the only difference between that is mu relative is equal to 1, but epsilon relative is equal to 4, and sigma is 0 in this material. Wave hits, some of it's reflected, some of it's transmitted. So we get E reflected and E transmitted. And we want to go ahead and analyze this. We want to figure out power and what the E fields are in both regions as well as the power density. So we'll start by finding first the intrinsic impedance in region 2. And that's technically the square root of mu over epsilon, which is square root of mu naught over epsilon naught times 1 over the square root of epsilon relative, because everything else is just the free space values. So that's going to be equal to eta naught divided by 2, because epsilon relative is 4, or it's 120 pi divided by 2, or 60 pi. But you can leave it as just eta naught over 2. Now the reflection coefficient at the surface would be equal to eta 2 minus eta 1 over eta 2 plus eta 1. Well, eta 2, if you factor out eta naught, you get 1/2 minus 1 over 1/2 plus 1, or you get minus 1/2 over 3/2, or minus 1/3. Go with me? I mean, this is pretty straightforward. After that, I get the reflected field. Now, the only thing I wanted was magnitude. The reflected field strength is simply reflection coefficient times the incident field. And it's actually gonna have, it's like negative 10, I think, I forgot exactly. About minus 10 point something, and that would be volts per meter, but magnitude, get rid of the negative. If you left it there, you get full credit. You didn't need it, because I asked for just magnitude, right? Then we get the transmitted field, and that's simply going to be the transmission coefficient, which is 1 plus reflection coefficient, times the incident field, and that's gonna be about 20, isn't it? 20 volts per meter. It's 19.99 something, but it's about 20 volts per meter. Then the next thing they want is the power. I think, did they want the incident power? Did I ask for them?
Yes.
You get that. So that's going to be simply 1/2 times the magnitude of the E field incident squared over eta naught. And the incident field is 30 volts per meter. I think I put that down here, but the incident field strength is 30 volts per meter. Eta naught's 120 pi. This is a straightforward calculation. Can you give that to me?
1.194.
Watts per meter squared. The reflected power, the average density of the reflected power, you can get a couple ways. You can find the reflected field strength, put it in there, square it, do the same thing, or you can just take simply the magnitude reflection coefficient squared times the average power density. It's instant, and you'll get it. And can you give that to me? Either one will work.
0.1329.
Finally, for the transmitted power, P average transmitted, well, you could take the P average incident, you can do it a couple ways, minus P average reflected, and that will give you the same answer. Or you can go ahead and say it's simply 1/2 over the magnitude of the transmitted power, which is transmitted E field squared divided by eta, which is going to be eta naught over 2. So the 2 will cancel. Either one will do it. Doesn't matter which one you use, you get the same answer. And can you give that to me?
1.061.
Watts. And is there anything else that I asked? I don't think I asked for H field. On a final, I'll probably ask for the H field somewhere, usually in media too. We might as well do that. How would you get it? I got the transmitted E field, right? How do I get the H field magnitude?
Divided by 82.
Right, 82, not 81. So, and you don't take the H field on this side multiplied by the transmission coefficient, you'll get a wrong answer. What you're gonna do is take H, this is gonna be equal to E transmitted over eta in region 2. And, can you just give that to me, just because I wanna make sure I state this explicitly today. So when people are watching this for the final, at least they'll have a note. Ready? That's it.
0.106.
Amps per meter. Okay. You get about that, guys? Make sure you know how to do the H. Okay, so that's problem 3. Problem 4. Well, that's, problem 4 is one I put on there just to, if you were in class the day before exam, okay, that was it. That was the problem I put on the board, so you had that with the 3D. So for this one, this is 6,600 ohms. This is 5 megahertz, you have it in front of you. And this is 500 megahertz. That's minus 20 dB, that's plus 20. It's a resistor. And this thing, the only thing you have to do is, in class, you remember this. This frequency is the lower cutoff frequency, and that's equal to 1 over 2 pi R times C, and that would be the parasitic capacitance. This frequency right there is the resonance frequency, or self-resonance, and that's equal to 1 over 2 pi square root of L times C parasitic. You found out there. This is L in the leads times C parasitic. So this is simple manipulation. If I want C parasitic, I say it's equal to 1 over 2 pi, and it's going to be R, which is 6,600, and it's going to be divided by that frequency, which is 5 megahertz. 5 times 10 to the 6. And can you give that to me? It's going to be about 4.8 something people.
4.823 picofarads.
Picofarad, right? Then, do y'all follow this? This is a straightforward problem. After that, now I have to get my L, so I can take F times 2 pi, square that, and then divide it there, so I get L would be equal to 1 over 2 pi F resonance squared divided by C parasitic. And what is that going to be?
2.10 times 10 to the negative 8.
Times 10 to the minus 8?
Yeah.
And that would be Henry's, or it's about 21 nanometers. All right. And that problem, if you come to the lecture before an exam, you find out there's always something I said that's literally going to be on it. I mean, verbatim copy of it. And I think that's as close as it gets. Finally, the last problem is the radar problem. We have about 2 weeks left. All right, we're gonna get through what we need to get through. All right, so for the radar problem, I have a target at a given range. The target has a radial velocity component, and can you give me this gain of the transmitter over here? 30?
30, yeah.
I made a mistake. And the range is 10?
10 kilometers.
And the target size, sigma RCS was 2, is that right? 2 meters squared. And let's see, what's the first thing they want?
Power density on the target.
Right. You always are gonna get that question from me. I always make sure people know this. So first I wanna find the average power density on the target, and that's always gonna be transmitted power over 4 pi r squared times gain of the transmitter. That's the linear gain. So I think that was 30 dB. So transmitted power, I forgot what it was.
40 kilowatt.
40 kW?
Yes, sir.
All right. So this is gonna be 40 times 10 to the third times gain of the transmitter, 30 dB, or it's 1,000, over 4 pi, and then R is 10 to the fourth, and you have to square that. It's a straightforward calculation. Can somebody do that?
31.838 kilowatts per meter squared.
Next, I think they want the power density returning on the radar, is that right?
Power receive power.
Total receive power, okay. So we can get the receive power, and the way we get it, that I'm gonna do it is I take the average power density. Some people just wrote the entire radar equation down, that's fine, but I'm gonna do it this way. Take the average power density we just calculated. Then I multiply it by the radar cross section. Now that's the total scattered power. Then I divide that by 4 pi r squared, because now that's spreading out isotropically. So divide by 4 pi r squared. Now I've got the power density back at that radar, right? Finally, I have to get the area, the electrical area that catches it. Think of it as a catcher's net. That's how I always do this. So that's going to be equal to lambda squared over 4 pi times the gain of the antenna. The gain of that antenna, I'll just put gain of the receiving antenna, which is the same as the transmitting antenna. Again, this is how I do that. If you want to do it your way, you simply take transmitted power times sigma RCS times lambda squared, divide that by 4 pi cubed r to the fourth, and you get the same thing. Times gain, sorry, gain squared, because the gain of the transmitter and gain of the receiver is the same. Y'all agree with this class? All right. And can you give that?
2.27 times 10 to the negative 11.
That would be watts. That's right. Next thing I think was the Doppler velocity, right? So, I mean the Doppler frequency. Doppler frequency based on was 2v over lambda. So now we got to get lambda. What was the transmitter frequency?
4 gigahertz.
4 gigahertz, that means lambda is c over f, 3 times 10 to the 8th over 4 times 10 to the 9th. That's 3/4 times 10 to the minus 1, or
0.075.
0.075. And the velocity on that one was what?
500 meters per second.
I was pleased to see almost everybody got that right. So it's 2 times 500 over 0.075, right? What does that come out, 10,000 something?
13,333.
Okay, and I think that was the test in a nutshell. There are a couple people that didn't take it, and you got an excuse for one, the other person, I don't know what to do with. There's only so much I can do. The average right now, as of now, is about 70, roughly, just shy of 70, but we had some, some people that really, unfortunately, very close, so that pulled the average down. Overall, most of the class did pretty well. We got 80s and 90s. Now, yes, we got it. We were talking about EMC last time, so I'm not trying to whiz through the class, but I want to just finish some of the things. And we get Bodie plot. By the way, is there supposed to be more rain this afternoon?
It's supposed to rain the rest of the week.
Today's Friday. Saturday only, Sunday?
I think Monday.
Oh, yeah.
It changes every day.
Well, it's without that. I think I told you that I read, maybe I haven't. I learned my lessons years ago. I looked out, they didn't have any real chance of rain, 10%. Few clouds in the sky, went out for a jog. I was doing about 5 or 6 mile jog. By the time I got back, I was absolutely soaked to the bone. And I was lucky that I didn't get struck by lightning. So things change rapidly in Alabama, and it's a bit unpredictable. So we're talking about EMC, and we went through and did resistor. First we did wires, internal inductance, external inductance is the partial inductance form. We did the resistance, the AC resistance wires. Then we did resistors, capacitors, and inductors, the high frequency model. After that, we talked about Bodie plot representation of the actual impedance of these elements. Then after that, Dr. Wentworth's book does something, and I'm not going to spend a whole lot of time on this, where he talks about when you have a square wave, which is very common for clocks and things like that that are used, what actually is the frequency response of it? Do y'all follow me on this, class? So let me just, I want to be absolutely clear about this. This is important because almost everything we have today, like that computer, runs on a digital clock. It's a voltage, it's a square wave. Not a pure square wave, but it's very close. So if you think about this, what I'm going to do is start with a single pulse. If I have a pulse, this is time, and I look at a standard pulse that has a width tau and a height 1, and call this V of t. It's going to be repetitive, but I'm going to start with just one of these pulses. Are you with me, everyone? So if I have one of these pulses, what is it? How could I represent it? Well, that pulse, I mean, what would the Fourier transform be? First, this function is commonly shown as either a rect of t over tau, or the pulse function p tau of t. You remember these from your signals and systems? Did you use rect or p?
Right.
You use the rect function? It's all right, they both mean the same thing. A rect function, the only thing you do is find out what the width is by that quantity, which is tau. It's whatever t is divided by. And it's 0, or it's centered at when the upper argument goes to 0. So you could have t minus 1 there, and it would be at t equals. T minus 1 goes to 0 at t equals 1. So that would be centered at 1 minute. But I hope you all follow me on what I'm trying to say. So for this, when I have a pulse function, or a function that looks like this, of width tau in the time domain, it goes, this is going to be my time domain function, f of t, it goes to a frequency domain, f of omega, of simply tau times the sinc of omega tau over 2. And the sinc function, sinc of x is really sine of x over x. And that looks like this. If you plotted the magnitude of sine of x over x versus x, it does this. This height would be 1, and it would be 2 first zeros here, but y'all, you remember sinc functions, class, everybody? I mean, if you haven't, you don't have to be immersed in this, just recall what a sinc function was, and it was really sine x over x. It's represented as sinc of x, right? And the key thing is the zeros. Where does the zero occur for a sinc function? Well, just look at this. The first zero, the sign is at zero, but actually if we evaluate this when it's zero, we have to use L'Hopital's rule, and we get derivative of sine cosine of x, derivative of x is 1, so cosine of 0, which you'd have to evaluate as x equals 0, is 1, and 1 over 1 is 1 right here. Next zero is right there, right? When I say a 0, it's where the value of the function is 0. So that would be when the sign is 0, right? When is sine 0? Well, at 0, at pi, right? You agree with me? So the first 0 here is pi. And this one would be minus pi. And the spread there would be 2 pi. Now, if you think about this, since the first 0, and I'm drawing attention to this for a reason. When I take a look at this, and I look at the frequency spectrum of this right here, tau of the sine, or sinc of omega tau over 2, I know it's going to look like this. And this is going to have a height of tau. And now I want this 0. I'll take the magnitude of that. That's going to go up like this. Well, this point here is going to be found when omega tau over 2 is equal to simply pi. Y'all follow me? We're taking the inner argument here, and I'm setting it equal to pi because I know from what I sketched out, the first 0 of the sinc function is at pi. I want to find this so I can get the bandwidth. That's my goal on this. So I'd say that's the case. That means what? Omega is going to be equal to 2 pi over tau. Y'all with me? And omega is always going to be 2 pi f. Omega is the radian frequency, 2 pi f would be a frequency in hertz. That means I can say that f is equal to 1 over tau. Now, does anybody have their book with them today? If you look in Dr. Wentworth's book in chapter 9, he's going to have something about bandwidth. And he's going to say that the bandwidth of a digital signal is about 1 over tau. I can spend a lot of time on this, but I'm not gonna. This is chapter 9. There you go. And somewhere in there, in the profound state. Well, he's got. It's not. These are estimates. I just want to show you what really happened. If you look at this for a second, now just to understand something, this is 0. The bandwidth itself would be, to the first 0, would be about 1 over tau. In Dr. Wentworth's book, he puts it at 0.5 over tau. And I'll tell you why. But bandwidth is kind of a mysterious thing. It's usually with radar, when we talk about any type of, like a beam width or bandwidth, it's always the half power points, where the peak power is reduced by half. Here, not so easily done. This is 1 pulse, that's the frequency spectrum. Y'all follow me on this one? Now the truth is, that's an absolute 0. The half power point would be about at this value, or at 1 over tau divided by 2, or at 0.5. So what he's really talking about in his book is this as the bandwidth, but it will only be from 0 out. So he's saying the bandwidth in his book is given as 1/2 times this cutoff frequency, which is 1 over tau. Can y'all follow me on that? That's the reason he does it. Usually when they talk about bandwidth, it's 1 over tau. For radar work and stuff, it goes to the absolute null. But in his book, he's talking about the half power point. So it's that. That's the only difference. Do you follow me? That's where this value, if you think that goes to tau, half of that is about the 0.707 value of the sine function, roughly. I mean, not exactly. That's how come he has it. But there's more to this, and I have to be clear about this. I want to make sure you appreciate what I'm doing. That's how he gets that information. Now, in truth, you don't have that. What you have is a huge number of pulses that represent a signal. And here I've got to show you a little something that's important that you may not see ever again, or until you're either your senior, when you're seniors in your some of the communications courses or some of the signal processing courses. But this is a really handy trick, and you can thank me for it, I believe. So, without getting too far into the weeds, y'all realize if you have any kind of a periodic signal, and I'm going to just use this one. This is a standard pulse signal. It's going to have a width tau, and it's going to be repetitive over a period t, or the PRI. This is a standard radar signature, you might say, for the baseband. Goes on forever. This is the time domain. You can say this is V of t, make it a hyphen. You all agree that that's about as square as it's a square wave. It's a repetitive square wave. It's used as a clock signal everywhere. And it has a huge amount of high frequency components. Now, if I have this V of t, better yet, I'll call it F of t. Because it's periodic, it can be expressed as a Fourier series. That means this can be expressed as a summation from n equals minus infinity to infinity of some c of n e to the j n omega naught t. Y'all remember that? That's a standard exponential Fourier series representation. It can be done for anything that's periodic. Do y'all remember that Fourier series, right? How many do? You've had to have it. If you're in this class, you had to have signals and systems. This is essential signals and systems, the Fourier series analysis. So if I have that, I know that first of all, omega naught is simply 2 pi over the period, repetitive period t, if you remember that, right? That's the fundamental frequency it's called. And to get C of n, usually you had to do something where you said C of n was equal to 1 over the period, the integral over the period of simply the f of t times e to the minus j n omega naught t dt. Y'all remember doing that? That was a standard way you calculated the coefficient c. With me so far? All right. Now, if I take a derivative of this, if I take df of t dt, which is usually just f prime, and I plot this versus t, what do I get over here? What's the derivative of this? It goes from 0 to a in an instant. What do we call that? An impulse function, don't we? It's called a direct delta function or an impulse function, right? Do you all remember? So now I'd get a spike here and would have a height a. It would be a delta function of t with a magnitude of a. Then when I hit tau, what happens? Now it goes from a back down to 0, or I have a negative spike down here. And that would be minus a, and this one would occur at delta of t minus tau. Y'all follow me? It's got the delta function turns on when the argument is 0. T minus tau is 0, t is tau, that's where the thing turns on. Its weight is minus a, correct? And it would be repetitive, it would go on forever. It would do this, then it would have this, and this, this, and this. It would be repetitive. Now coming over here, because it is a repetitive series, I could say that f prime itself is equal to simply a summation of, I'll call it Cn prime, from n equals minus infinity to infinity, of, and this would be equal to e to the j n omega naught t. And what I'm really doing is saying, even though it's impulses, it's a repetitive series, right? It repeats itself every period. So it can be expressed this way. And my Cn prime is 1 over the period times the integral from 0 to t of, and it would be my f prime times e to the minus j n omega naught t dt. There's going to be a reason I'm doing this. I know this looks like it's getting really abstract, but there's an absolute reason I'm doing it. Y'all agree with that? Because it is repetitive, I can capture these coefficients by just taking the f prime, the value of the derivative. Now, what happens if I integrate a delta function of t dt from minus infinity to infinity? Can anybody tell me?
It just equals delta, right?
Huh?
That just equals the value, delta, whatever delta is.
The coefficient of delta, it's 1 in there, right? And that's the thing I was gonna say is, that's the truth. Whenever the delta function, if you integrate through a delta function, you get 1, that's it. Matter of fact, the integral of delta of t from minus infinity to t, make that t prime dt, is simply u of t. That's it. If the delta, if you're at u of t, if you're at negative values of t is 0, right? Okay. Now, the next thing, and I'm just gonna move on and get to the point. So if I have an integral of f of t times delta of t minus tau dt from minus infinity to infinity, I want you to notice something. The delta function itself is 0 for all values of t except at tau. You all follow me? So what I can do is say this is really equal to the integral of f of t times delta of t minus tau, but it will be from tau minus some delta t to tau plus some delta t. Now what I've done is eliminated a good chunk of that integral, and I'm just below where the delta function turns on and just above it. Do y'all follow me on this? Now what's really gonna happen here is this is gonna turn on at tau, which is just an instant. I mean, it's just after delta t less and delta t plus tau. So this is really means f is simply gonna be f of tau, right there, times the integral of delta function, which is 1. My real point is this is called, the delta function simply extracts or samples the value of f of t at the point where the delta function turns on. That's all that happens in this integration. Can you appreciate this, guys? With me? All right, so when I look over here to my c of n prime value, that's 1 over t. Now look, f prime is a whole bunch of delta functions, right? Now I'll only do the first 2 because it's going to be repetitive after that, and this integral only goes from 0 to t. So now it's 1 over t times the integral. The first delta function is a delta t minus a times delta of t minus tau. Those are the first 2 times e to the minus j n omega naught t dt. The only thing I've done here is I've replaced f prime with a delta function notation. I have a delta t minus a delta t minus tau, and it's got to be times e to the minus j and omega naught t. Follow me so far? All right, keep watching. I'm going to do it up here so you can see it better. I got some time to do it. So now, when I look at my c prime, c in a prime, it's 1 over t, and now I want to make sure I've got everybody's attention. I'll show you how simple this is. If you look at this first part, where does that turn on? When does the delta function become infinite? Right here. T equals 0, right? It's always the delta function. The argument the delta function goes to 0, that's where it goes to infinity. All other values are simply 0. Just try to be clear about this. If you were graphing delta of t minus tau, it would look like this. When t, if this is t and this is tau, it just goes to infinity. That's what the delta function turns on. That's a term I use. It means it becomes non-zero. Well, here, it turns on at 0, right? The function that's next to it in sampling is this e to the minus j n omega naught t. So you replace t with 0 and evaluate that function. That means this is going to be 1 over t. And the first part would be a, right? Times this. Well, what is e to the j 0 is? E to the 0, what is e to the 0? 1. So it's just times 1. Now this turns on when? Just look at it. at tau, when t minus tau is 0 or t equals tau, right? So now I replace this value of t with tau, and I get minus a, and it's going to be times e to the minus j n omega naught tau. Are you all with me so far? I'm just showing you that that's the value of Cn prime. Now that value is something, and it doesn't look real familiar to you, but believe it or not, you're going to see that this thing's going to become a common function. All right, so if I look over here, I see that really my Cn prime is going to be a times 1 minus e to the minus j n omega naught tau. Okay? And I'm going to work on that in a second and turn it into a normal function that you'll appreciate. But now I come back over here. And just, I want to make sure that you write it down. I'm going to post a lot of information about this. It'll be on OneNote, a very clear description of what I'm talking about today, so you won't have any kind of uncertainties. This isn't in this book, by the way, but it's very valuable. You're going to see that. So when I come over here and relook at this, I want to show you something. I'm just going to erase this. So I have a little boardroom. Now, if you take a look at this, this is C of n, right? Right. And I look at this as f of t. Now, what is f prime of t? That's the derivative of this with respect to t. You all agree with that? Now, the C of n's in there are constants. So when I take a derivative of that, I end up with a series from n equals minus infinity to infinity. A derivative of that is still going to have C of n in it, right? But then it's going to have the derivative of e to the j and omega t with respect to t is going to bring out a j n times omega naught times e to the j n omega naught t. Are you all with me on that? I've just taken a time derivative of that. C of n stays. The only thing that's going to be a function of time is this exponential, so I pull out a j n omega naught. With me? Now, that right there is, remember I just solved for the C of n. This is the impulse series. Well, that's equal to C of n prime times e to the j n omega naught t from n equals minus infinity to infinity. And if you look at this, remember, because it is repetitive, it can be expressed as a Fourier series, right? We calculated Cn prime, didn't we? Just that one right there that I'm going to mess with in a second. That means this is equal to this, or I can say my C of n is just equal to C of n prime over j n omega naught. With me? So if I can get this, if I take the derivative of this series and their delta functions, I can easily represent the coefficients of the delta function series and then divide it by j and omega naught. Now I have C of n. Please just appreciate it. It eliminates the need for integration, is what I'm getting at. It makes problems simple. You don't have to do integration by parts and all those crazy ones. If you can take derivatives of the infinite series with respect to time and get impulses, and you can. Now, back, just follow me on this. That's what I have for C of n prime. Now I'm going to make this into something that's recognizable. When I look at C of n prime, that's a over t. Now, I factor out an e to the minus j n omega naught tau over 2. So I'm going to go ahead and factor out e to the minus j n omega naught tau over 2 out of that. And I'm left with e to the j n omega naught tau over 2 minus e to the minus j n omega naught tau over 2. Everybody with me on that? Anybody want to guess why I did that? God, I know there's people who know this. What is sine of theta equal to? E to the j theta minus e to the minus j theta over 2j, right? Or I could say 2j times the sine of theta is equal to e to the j theta minus e to the minus j theta, right? Come on. Are you with me on this, guys? Well, what do you see here? Theta is just what? N omega naught tau over 2, isn't it? In that proof right there? Y'all see this? So what I can do is say that my C of n prime is equal to A over tau, and it's going to be times this quantity, e to the minus j n omega naught tau over 2. And then I'm going to have 2j times the sine of n omega naught tau over 2. I've done it for a very specific reason. Sine is a function I understand. I know what it looks like. I don't know what that thing looks like, at least not easily. Are you with me, class? Okay. Now, I have C of n prime. This is the series I want. I want the coefficients for this series. But I've got that. Now I come over here and divide it by j and omega naught. Do y'all follow me? All right. And I need boardroom here, so I'll tell you what. Let me do it right here. So now I say my C of n is equal to C of n prime over j n omega naught. C of n prime is that. So that's equal to A over t, it's just a coefficient, times e to the minus j n omega naught tau over 2. Then it's times the sine, times 2j, pardon me, 2j times the sine of n omega naught tau over 2, right? It's that, and then I have to divide that, all this by j n omega naught. Just follow what I'm up to. I'm doing this, taking the Cn prime, after I turn it into a sine function, the sine of n omega naught tau over 2, divided by j n omega naught. You with me, everyone? Now, I'll even erase this so you can follow me. This is Cn. This is what I'm at. Now, you all see the j's cancel, class? Can you see that? J on top, J on the bottom, they cancel, so I'm going to get rid of it. Now, to fit the form I want, to get a sinc function, I'm going to divide top and bottom by 2. So this is going to be divided by 2, and that gets rid of that 2. Are you with me? Now, focus on this. Isn't that sine x over x form? So I can replace that with a sinc function. Now I can say my C of n right here has a magnitude A over tau, or A over the period, times, not magnitude, value, e to the minus j n omega naught tau over 2. And now it's going to be times the sinc of n omega naught tau over 2. That's important. So now I've got the coefficients of this infinite series versus frequency, or versus the actual harmonic level. Remember, omega naught right there is called the harmonic frequency, first harmonic or fundamental frequency. N times omega naught, for any harmonic, you can see the value of C of n, and that tells me the amount of the signal strength at each one of those frequencies in the frequency spectrum. Now, I'm just going to show you something, because now I'm getting close to the amount of time. And I'm going to do it here. So now, if you take a look at that, and you were to plot in the frequency domain, as a matter of fact, let me do this for you. Since this is C of n, I'm going to put it in terms of f. It would be A over tau over t. And I'm just going to take magnitude. I don't care about that phase. And that would be times the magnitude of the sinc, S-I-N-C. And it'd be, omega naught here is 2 pi f, so it would be the sinc of n times pi times f times tau. If you replaced omega naught by 2 pi f, the 2's would cancel, you'd have a pi in there. And now this is versus just frequency. So remember, in this, I'm sorry, F naught, which is the fundamental, and F naught is simply equal to 1 over the period. follow me on that, class? Now, the reason I did it is this. When I look at the magnitude of that function, so this is the magnitude of C of n versus f, what I can see is that as I increment n, all right, I'm really taking a look at sampling the sinc function's envelope at different values. All right, now just follow me on this. So if I plot this, I know the sinc function is going to look like this in terms of the magnitude. And I know where the first zero is, right there. That's where this function is equal to pi. Where the first zero, right there, will be when n times pi times f naught times tau equals pi, or when really n f naught here is going to be equal to 1 over tau. And then, because f naught is 1 over the period, or should be, no, I'll leave it like that. Anyway, that's where the first zero is, and here's what actually happens. I'm not going to have enough time to go through all this. What you have is, when you look in the frequency domain at where the signal is, this is going to be proportional to the voltage strength, not the power. This is how it looks in the frequency spectrum. And you can see, when you have a square wave, all right, a square wave like that, you have frequency components all over the place, right? Here, the key thing is, when they talk about bandwidth, is usually this range here to the first zero, because that's where most of the energy is, most of the things. There are some high frequency things, but this really is sort of the important thing when we're doing any type of work with like radar, EMC analysis, anything that involves digital signals, and you want to talk about the bandwidth or the frequencies that you have to be concerned about. They're limited to this point in the frequency domain. And that point is simply going to be NF naught equals 1 over T, 1 over tau, 1 over the on time. And I'm going to spend more on this, but the power actually is proportional to the squared values of these values, C of n. And I'm going to give, I know it seems overwhelming at first. Don't worry, I've sat where you are, I know what it's like. It's going to seem a bit much, but you're going to see this come together very quickly. I'm going to give you some reading and give you some problems for Monday. And on Monday, we'll do justice to all this, close the door. It will not be as bad as you probably are imagining it is. You're not going to have to do all sorts of crazy FOIA analysis. Right? You just have to appreciate you need to do that to get to the final, I guess, answers of reports. And I'll give you some problems in the meeting. But please don't fight. And listen, if you had a bad time on the test, don't just, sit there depressed. Final exam is worth more. You still got a chance to do it. I'm trying to encourage you. I know I hate the problems. But overall, the class is pretty good. Pretty good.
All right, Dr. Baginski. On the syllabus, it said that there's a MATLAB project.
We'll talk about that. I really, in the summer months, you got 10 weeks. It's going to be related to some stuff we're doing here. Right? And I know with Dr. Wynn, we want you to do a major project. The problem is,